then the first thing is to potentially talk about the solution of your homework assignment. So does anyone want me to talk about it, or you guys are all going like, yeah, we got it. Want to talk about it? Okay, we'll do it. We'll do that. All right, so let me get to the right class first, and then we'll get to the solution. All right, so the question or the homework assignment is resolution and proof by contradiction. There we go. All right, so the first thing we need to do is to negate the proposed theorem. So the first one looks kind of nasty. It's this one here. The second one looks less nasty, which is this one over here. All right, so the first thing we need to do is to, the first thing I'm going to do is to copy this into a text editor, and I'm just going to do all the derivation inside the text editor here. So do a paste, and then make the screen larger because this can be lengthy. All right. All right, so we are going to convert this expression into a CNF. There are, once again, two ways to do it. You can use Boolean algebra. You can also use the truth table approach. So the truth table approach, can also be time consuming unless you have a parser to turn this into spreadsheet, formulae, and then just use a spreadsheet to do the whole thing. So you can semi-automate the entire thing using that approach. I'm just going to solve it using Boolean algebra. Okay, so we'll solve it kind of the old-fashioned and slower way. The first step is to get rid of all the implications. So the way to do that, usually what I do is I'm just going to copy and paste, and then I will work with the implication, turn that into an or, and then make sure that I negate the left-hand side. And the same thing over here, turn the implication into an or, and then negate whatever is on the left-hand side like so. So this is using the definition of implication. Once I have done that, then the usual thing that I do is to see if there's anything that I can simplify. So double negation can all be simplified out. We only got one double negation here. This is not a double negation, okay, because one negation applies to the conjunction of the two things inside the conjunction. So this is not a double negation. We cannot simplify that out. Yes?
So, does it matter if you negate it after you change it to a CNF or negate it now and then change it to a CNF?
Well, the restriction of the CNF is inside the CNF, inside a disjunctive element of a CNF. The only thing you can negate is a variable.
No, I mean the entire thing you're supposed to negate it, right? Because
Right. Yep, I forgot that. Yep, you're right. I'm supposed to put a big, huge negation all the way out. You are correct. I forgot about that. All right, so let's do that. All right. Well, it doesn't affect too much here because I'm going to keep the negation on the outside and just do the rest like what I did before, and then I can apply the negation later on. Um, it's up to you. I mean, you can, because this negation is applied to the implicit conjunction, which is here. So you can do it separately, or you can, kind of do whatever is inside first and then do the De Morgan's law. Um, well, I mean, we can do it either way. So let's go ahead and use De Morgan's law first. So if I use De Morgan's law first, then I end up negating each component in the conjunction. And I can't match parentheses. Okay, wait. Yep, okay, so there's another one here, and then put an or here. And as a result, I don't need the outermost parentheses, so I can get rid of those two. Let me see if I can turn on parentheses matching, because that can be very helpful. All right, so view, highlight, matching brackets. I think that should do it. Woohoo! Yes. Okay, that's very helpful. Okay, there we go. So now we can get rid of the implication. So we have not, okay, I'm going to copy, paste, and then do what I did a little bit earlier. You know, turn this to a or, and turn that to a or, but negate the first part like that. Is that okay? All right. And then we can simplify. So now we simplify the double negation out. There's only one double negation I can simplify out, which is this one. All right. Um, I know I have to apply De Morgan's law, because of this negation here. So that's the next thing I can do. I can also use De Morgan's law on this one, or use De Morgan's law on this one, or I can also use De Morgan's law on this one, which is applied to the implicit conjunction inside the parentheses. So there are quite a few, De Morgan's law that I can apply. So we'll go ahead and apply several at the same time. As long as they're not at the same spot, it will still be easy to tell. So I will first, deal with this one and turn it into a disjunction with not P, not R, not T. So this whole thing becomes a disjunction with not P, not R, or not T. So checking the parentheses, making sure that everything is good. And then this one turns into a disjunction with not P, oops, not P, or not, oh, I think I just messed up. Okay. All right, so that turns into not P or not Q. And then this part here, yep.
So when you got rid of the implication on
Mm-hmm.
line 3,
Mm-hmm.
right? Um, why is it? I thought when you get rid of the implication, you negate the left-hand side and then you or.
Yep. Oh, this is supposed to be an or. You're correct.
That's what I was.
I mistyped. That is supposed to be an or, so this is supposed to be an or as well. And that is also supposed to be an or. There we go. All right. And then we can now simplify. So copy and paste and take out all the double negations like that. Okay. And now we can move on to the next step. All right, so the next step, I still have one De Morgan's law to apply other than the one on the outside, because this particular negation applies to this particular or here. So I can, once again, use De Morgan's law. Did anyone use the other approach, which is the truth table approach? No? You did? Okay. How was it? Because you still have to put in the entire expression into a spreadsheet or hand evaluate the whole thing.
Converted it to a DNF first, and then it was a bit easier.
Okay. All right, so this negation is distributed inside to this guy and also this guy. And then the or becomes an and, so it goes away, or at least in terms of notation. Okay.
I have a question.
Yep.
What if you do a couple of De Morgan's law at the same time?
You can do a couple of De Morgan's law at the same time. Yep. But if I make a mistake, it just makes it harder to track. So that's why I usually don't do that. So this one becomes not P, not Q. Get rid of that. And then the other side becomes not R, not S. Oops. So good. So that is now replaced. And I can do simplification in place, but I'm going to start a new line because it's easier to start a new line. Things are easier to track like that. All right. And I think somehow I lost a parenthesis. Somewhere I lost a pair of parentheses. Yep. So this is where I lost one. Because we are supposed to have a overall parentheses around the entire thing. So I've been missing. Hmm. Nope. All right, so it has to be on the other side. Oh, I performed the I took care of this negation first with De Morgan's law. I forgot about that. Okay, so now everything is still looking good. All right. Let's see. How can we simplify this?
De Morgan's with the outside negation.
You mean this negation?
Yeah.
So that will help take care of a little bit. Okay, well, we can do that. I was trying to simplify what is inside a little bit first, but we can do this first. So it will negate. So we distribute this negation to this one and also this one. But this time, I need to put extra parentheses in, like so, and this becomes a conjunction. So that means next I have to take care of this particular disjunction. I mean this negation, which is applied to the overall operation is a or. So I only need one pair of parentheses. I can delete the other one. All right, so let me double check and make sure that this makes sense. It does, okay. All right, so now we have another De Morgan's law to apply, which is this particular negation, and it is applied to the or, which is here. So we get rid of that, and we have negate this one, and this time I do need parentheses now because I'm now moving on to this level. And then this has to be a and. Simplify. And we have another De Morgan's law. So this negation is applied to the conjunction, which is here. So if I use De Morgan's law, that becomes the negation of this, and then the negation of that, and then with the or in the inside. And then we can take care of this using De Morgan's law. So that becomes not P and not R instead of that. And then this one becomes not P and not R and not T instead of that. And I'm just checking the parentheses to be sure. Okay, so we are still good. All right. And then we can simplify. double negations are gone. All right.
There should be a negation.
Hmm?
There should be a negation after that disjunction, because the Morgan's law applies to the right of the outside conjunction or disjunction.
Mm,
And that should be, so on the far right side, what's
on
in
the far right
parentheses,
side? Uh-huh.
that should be a conjunction, not a disjunction.
You mean this one?
Yes. And that should be negated. What's to the right? Since you distributed the negative, or you applied the Morgan's law to the outside negation.
But this OR was introduced in the first step. That OR is the same as this OR here.
Right, but you distributed in the outside negation the entire, or is that just the first part?
Okay, so let me show the line numbers. It makes it easier to designate which line. So show line numbers.
So line 10,
Line 10.
you did the Morgan's law to the entire thing because that negation applies to all, that outside negation applies to the whole thing. That's the initial negation.
This negation?
Yeah.
This negation is not the first. It's not this negation. This negation is already taken care of. So this negation is actually.
The parentheses at line 7.
Huh?
You dropped a parentheses at line 7.
On line 7?
Yeah. Maybe I'm wrong.
Nope. Line 7 is fine. Are we still doing okay or not?
It's that the right hand side is a completely, the dividing line is that disjunction. Right?
On which line?
On the line 15.
On line 15. And
that
which
disjunction is the dividing spot, right?
that disjunction?
It's
You
on
mean
the very top, right?
you mean this disjunction?
Yeah.
So this disjunction appeared after the first application of De Morgan's law.
Yeah, but you hadn't applied that outside negation.
This is the outside negation, which was applied to the implicit conjunction here. All right, so at any point of this particular derivation, if I need to find out whether I made a mistake or not, how would I go about doing it? Hmm? Do you guys remember the 5 nested loop thing? So what I can do is I can type in the first equation, I can type in what I have now, and make sure that for all the rows in the truth table, they come out to be the same. So the truth table approach, which at least one person used, is actually not as nasty as it seems, because what it does require is the entering of the first equation like this one. So once you have that done, then the rest can be automated, can be done with the program, because we can then pick out which rows are zeros. But I'm a little stubborn. I want to continue to use Boolean algebra, but I have no idea whether it's still right or not. I actually have a program to test to test derivations to see whether the equations are still working or not. Let me see if I can find it and use it. Or do you guys not want to do that?
I'm interested.
Hmm?
I'm interested.
Okay. All right. So let me see if I can find it. I'm on the other side of the screen. Or do you guys want me to just use a program, to test all of this stuff here? That's another way to do it. Yep.
I have a question.
Mm-hmm.
So on line three,
On
how
line
you
three?
negate it as the third time? Shouldn't you be doing the same to like after the plus sign to negation of Q plus?
So you're asking, should I also use a negation here?
Yeah.
The answer is no, because when you deal with the implication, you turn the implication operator into an or, but we only negate the left-hand side. In other words, okay, if you have something simple like this, A implies B, the way it translates to is not A or B. So B is not negated. Yep.
I have a question for line 7.
Line 7?
Yeah. When you negate the P plus Q and then the other side of the OR, why do you take out the OR?
Because that's De Morgan's law. So De Morgan's law allows me to distribute the negation to the components of either and or. So in this case, we have an or here, right? So that's why, I'm distributing the negation to each component, and therefore we have the negation of the first component and also the negation of the second component. But when you apply De Morgan's law, the original or becomes an and, or if you start with an and, it becomes an or. Are we still okay so far? Okay, so let me continue to find the tool that I have written. That is curious. All right, so let me look up the JS here. Coins, Boolean expression. I think that's okay. I am going to give this a try first and see whether that's the right way to run the program. Give me a second. Okay, so I can now show you the result. It's a little bit too long. All right. So let me, okay, Control C, get out of the program. Oh, it's still continue asking me. Okay, let me do it one more time. There we go. So what I'm doing is I'm copy and pasting the entire derivation into the program. And now that this is all done, so what I'm looking for is, okay, so there's this problem with syntax, expecting a conjunction term at this thing here. All right, why is it? It does say everything is the same, expecting a conjunction term, new expression is the same as the previous one. And if I look at the pairing of parentheses, they're all paired up correctly. All right, so the other way to check this, okay, let's go for the other way to check it. Okay, this is the brute force way to do it. But this is also something that everybody can do as long as you have taken CISP440, you can do it this way, which is the same way that we did last time, if you remember. We got integers P, Q, R, S, T, P, Q, R, S, T, like that. And then we have 4, P equals to 0, P is less than 2, plus P, and then we paste this 5 times, so for the 5 loops. So we have P, Q, R, S, T, and so at this level, we are going to have all the 5 variables already determined. So now we need to evaluate the 2 expressions. So to make things a little bit more clear, it is usually good to define those expressions differently. So I'm going to define the original. So we say int original, int p, int q, int r, int s, int t. And that's going to be this one over here. But there's no easy way to translate that. So I'm going to have to define the same thing as last time, which is a implication. So implies x, y expands to not x or y. Like that. And put this entire thing also in parentheses, just in case it becomes a component of something else. All right, so now we need to encode this entire thing into that form. So we have a negation on the outside, and then we have implies. That's the first implication. The first implication is ended with the second one. So we have a and then we have a second implication of something. And you can see the way I type it is, by structure. I'm not, sequentially entering everything because that would be even harder. We have the negation of S as the left-hand side of the first implication, and then the other side is going to be not Q or P or R, and the negation of P and R and T. Okay, matching all the parentheses. Okay, so we now move on to the second implication, which starts off with not P and not Q as the first parameter. And then the second parameter of the implication is not R or not S. All right, so I'm still missing something. All right, so let me check the implication. This is the first implication. Not S is the first component. The second component is not Q or not Q or P or R, and not P and not P and R and T. Just trying to make sure that I match. All right, so there's an and here. We are taking the implication of the first implication and end it with the second implication. So that is correct. After the second implication, this is the close. Oh, okay, I see where the problem is. I have one extra open paren here that is not needed. That's why. Okay, so this is all good. So this is our current function. So what we have right now is the last one. So I'm trying to be brave here and only check the last one instead of the ones intermediate. So the last one is open, okay, not S and Q and not P and not R, or P and R and T, close, 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 or not P and not Q and R and S. Okay, so I think that's it. Yep. Semicolons. All right, so when we get here, we need to make sure that the original is still the same as the one that I have currently. So now I have to say if original PQRST equals to current PQRST.
You accidentally flipped the T and S.
Hmm?
You accidentally flipped the T and S in the
Oh,
function.
transposed. Yeah. There we go. And if they are not the same, we're in trouble. So it's only when they're not the same that I need to complain. So if they're not the same, I have a printf statement that says P equals, Q equals, R equals. I mean, we can probably just say complain and say not the same. All right. And then we can format this a little bit better. There we go. All right. So are we okay so far? I mean, at least understanding what I'm trying to do. All right. Okay, so we have gcc-g-o check.c. All right. Complaints about printf. That's because I forgot to pound include standard io.h. There we go. And everything checks out. So the derivation is still good. But this is one way, to kind of proceed with caution is, you just, check occasionally. You don't have to do it with every single step, but every 5 step, every, 10 steps or so, just kind of run it and check it. Are we still doing okay so far? All right. Now, of course, you can also say maybe the program itself is at fault. Okay, so we can try to introduce a problem. In other words, I intentionally make a mistake. Okay, better save this one first before I make that mistake, because otherwise I cannot remember how to undo it. So let's just say that this wasn't there. Yep.
In your loops, you just incremented P all over.
Hmm?
In the loops. Yeah, the loops don't do anything.
The loop is only incrementing P. Then how is it going to exit? Oh, because it's only checking P.
Yeah.
Oh, you're right. Okay. You caught me. I think I have just illustrated why copy and paste is evil. Because if you forget to modify, copy, and modify, if you forget about the modify part, it's not going to work. All right. Okay, so there we go. Oh, I better redo the not make the mistake first. Okay, so we'll put the correct code back in and then rerun the code. Nope, we're still good. But thank you. That was good. Okay, I totally did not catch that mistake of mine. All right, so this time I'm going to inject a mistake in just to make sure that the code is checking correctly. So this time it should complain a bit. So with GCC and yep. So this time it complains because by forgetting that negation of S, on the left-hand side, the results, do not match anymore. So I can I have some confidence that the program is working, which also means, I have some confidence that, up to this point, everything is still good. Are we doing okay? All right. All right, so we move on. So we can no longer apply De Morgan's law. There's no negation of n and no negation of 4 left to apply De Morgan's law. So all we can do at this point is distribute. So we can now do the distribution. So I would probably want to distribute the Q to this particular OR first. So that means this Q is ANDed with each of these components. So PQR, PQR, and then the Q is gone. And we can, I'm just looking at the number of parentheses. I think we can take out one pair of parentheses without changing the meaning, like that. Are we doing okay so far? All right. So the next step is also a distribution. So we have this not S on the outside that we can distribute to everything in the inside. So the not S gets distributed here as well as here. I'm trying to keep the alphabetical order if I can. So that is that. So now we have the opposite of a CNF. I have a DNF. So in the case of a DNF is you can do the distribution or you can kind of go for the truth table approach because to do the distribution this way is really nasty because you have to okay, these parentheses are no longer needed, but this is a DNF instead of a CNF, which is kind of opposite to what we want. Um, every time you have a DNF and you want to convert it to a CNF, the only way to do it is to use distribution, and it's going to be pretty ugly because I'll show you what I mean by it's going to be ugly. Um, because if you have A and B or C and D like this, which is a DNF, it's a disjunctive normal form. To convert this into a CNF, you have to distribute, but this time it's going to be a FOIL, which means that we end up with A or C and A or D and B or C and B or D. So it's the product of the number of terms inside each CNF. We got 5 here. We got 5. We got 1, 2, 3, 4, 5. We got 5. We got 5 here, 4 here. So that's 20 terms. And those 20 terms would then also be distributed to these 4. So we can potentially end up with 80 terms if we just do it blindly and mechanically. So so this may not be the best way to do it. Yep.
I did the distribution.
Uh-huh.
I got like a conjunction with one for some of the terms.
Mm-hmm.
Can I just ignore? I just ignored the one. Is that equivalent?
A conjunction with one, you can ignore the one, but you have to keep the rest.
Yeah.
Yep. If you have a disjunction with one, then it becomes just one. If you have a disjunction, if you have a conjunction with 0, it becomes 0. So you can simplify along the way. So we can already identify not P um, or P is just 1, so that one is just not really meaningful. Q or Q is just Q, so that one is relatively easy. But you still have all of the other ones like not P or Q, not P or R. So you still end up with a lot of terms in this case. Is that okay? So what would be the best way to do it? The truth table way. Okay. So if I want to use the truth table way and I have this check program already, how far am I from converting this into a truth table approach? In a different condition, right? Okay. So let me get back to what I want to do now. So let's just say that I'm giving up on the derivation approach because this is not a dead end. It's just a nasty way to go about doing it. So if I want to use the truth table approach, I have the code already like this, and I'm fairly confident that my original function is correct. So what do I need to do on line 23 and line 44 so that I end up with the answer that I need? Yep. Starting on line 23.
You need to change it to if original.
Is false. Because when you work with the conversion, it's everything that is false.
Right.
Yep.
Yeah, you're trying to negate the.
Yep.
I see. Yeah, if the original is false, then print the.
Yep. So we have to print the values of P, Q, R, S, T, right? So we have to say P, Q, R, S, T. Or better yet, okay, so here's the better way to do it. It's still kind of nasty, but I think we can do this. So I'm just trying to think about how to do this. What is the best way to do it? It's not an array, which is the reason why I can't do this with a loop. Well, okay. I'll do it the not so obvious way because I don't want to waste too much time to write the actual function to do it automatically. So we'll say p q r s t equals to %d, 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 backslash n for line feed. And then the %ds would be p, q, r, s, t respectively. So this will tell me when PQR, what the values of, okay, what are the values of PQRST in order for the expression to be false. And that's going to be useful to me because I need to negate them too. Okay, but that's the next step. Okay, so
You need to change it back to the original. You commented out the correct
uh, I'm not using current, so it's not going to be, this won't impact anything because I'm not using current at all. Because in the expression, I'm only trying to check to see if the original is false or not. But it's printing out a lot of entries, more than I expected.
Is original the original theorem?
Yep. No, the original is actually the negation of the original theorem. Let me double check. So the original is negating the first implication. So it is the negation of the theorem.
Okay.
Or at least I think so. Let me double check on this side. So we're working with this one. Yeah, so it is the negation of the theorem already. You did not see that many items?
I did not.
Oh, yep.
I tried the truth table approach, and I got like 27 different entries.
This looks like 27.
Yeah, so that was very
Some of these can be combined. If you use linear algebra, you can actually combine some of these. Like the first two rows can be combined because you can see that t does not matter. So you can combine some of these just by looking just manually. Are we still doing okay so far? All right, so do you guys still remember how to look at this and convert it into the CNF? When you see a zero, yep.
You take you conjunct all the disjunctions of the true variables there. So um, since those are all false, they're all part of the CNF.
Okay, so let's go ahead and do this step by step, okay? Because we want to look at this and convert it into a CNF. The question is, how do we convert this into a CNF? All of these, okay, the first row, for instance, is telling us that when P, Q, R, S, T are all false, that particular row should be false, right? And then the second row is telling us, if P, Q, R, S are all false, but T is true, then that particular row should also be false. And but only for that row. For all of the other rows, it'll be true. Okay. So that means if you okay, so looking at this one here, okay, let me. So we'll just take one row into consideration. Take one row that is not so obvious like this one. Okay. So this is basically saying, when P is false, so we have, okay, not P, not Q, not R is not negated, S is negated, and then T is also not negated. Okay, so if you look at this expression and you look at the row that I just highlighted, which is this row here. Okay, so when P is false, Q is false, R is true, S is false, and T is also true, what would be the value of this expression?
False.
It'll be true. It'll be true. But how do we turn this into false?
Negated.
Negate it. Very good. So we, oops. So we negate this. And what do we end up with after we negate this? Remember, each row is supposed to correspond to a disjunction. So we're looking at this thing here, and we look at this, and we say, we want to turn this into a disjunction.
P or Q or not R or S or not T.
Yep. So we apply De Morgan's law. So we apply De Morgan's law. This becomes P or Q or not R or S or not T. So in that case, this disjunction is going to be false, but only for this particular row. Okay? So we double check it, okay? We need to double check. So we say P is false, okay? So far the disjunction is false. Q is also false, so far it is false. R is true, so not R is false. S is false, so far it is still false. And then T is true with the highlighted row, so not T is going to be false. So this entire disjunction is going to be false, but it's only going to be false for this specific row. For all of the other rows, it will be true. Is that okay? Right? So this is how we can look at each row and come up with the disjunction corresponding to each row. And then we just make a huge conjunction out of these rows, and that will be the answer. Well, it would be the answer to the CNF corresponding to the negation of the theorem. And then we perform resolution. But we don't have to do, okay, so you can look at this whole thing, and we can combine several of these. Like the first two rows can be combined. Let me show you how to combine the first two rows. Every time you see a negation, it means we want the non-negative version of the variable in the disjunction. So the first two rows combine to P or Q or R or S, and then T is not even here, because you can see whether T is false or true does not matter. The other four are the same. Is that okay? So we look at the next two rows. It's also going to be, we can apply the same thing. So P or Q or R, or in this case, not S. So when you have these two, you can also say, oh, maybe S is not important. Because the first four rows is basically looking at all the possible ways for S and T, and they do not matter at all. So that means when you have these two in a conjunction, then you can simplify to just P or Q or S. Okay, that's for the first four rows. Any questions? And then we look at the next two. You can basically see how the next two, we can take out T again. So T does not make any difference. And then we look at the next two. Okay. And then we look at the next two. I think T does not make a difference here. T does not make a difference here. T does not make a difference here. Not a difference here. So it would look to me that T does not make any difference whatsoever except for one. Yep, okay, so except for this one, this is the one where t actually does make a difference because you can see, only 11100 is here, but 11101 is not here. So this is the only one where t actually does matter. Are we still doing okay so far? So what was the conclusion? Did you guys go all the way to the resolution step? Okay.
For year one, I got that it's valid.
Mm-hmm. And then the other one?
I got it's valid.
I think one resolves and one does not.
For the
Yep.
for the first one, I got that it was invalid.
The first one is not a
It's
theorem.
not a theorem.
This is not a theorem, and then this one is a theorem.
Yeah.
I think that's what they're supposed to be. It's okay. When I grade it, I'm just looking at the steps that you take. Yep.
Yeah, the complexity of the first one was way more than the second one. The second one felt like I was bashing my head against the first one for so long, and then I started the second one, and it was like, no.
Did you try the
No, I was
the
just trying to
table?
brute force the Boolean algebra,
I see.
which was why it was frustrating.
But that's the nice thing about Boolean algebra is you always have that alternative of using a truth table. Yep.
For the resolution, when you're picking a term, a conjunction, do you have to go through each like variable sequentially? Like you were showing it in the previous example in class, and you went like if it was not P or R, you look at you find a P to cancel out the not P, and you go to R. Like, do you have to go sequentially within the super CNF, or can you just look and see where you can get those elements?
Oh, you can sequence the resolution any way you want. So if you can eyeball the whole thing and you go like, I can see a shortcut, to get to the zero, you can go for the shortcut.
Okay, and it doesn't in the super CNF. It doesn't matter which side or where you got it, whether it was from the.
That is correct. It does not matter. Because you basically have three components to the super CNF in general. You have the one part that represents psi, which is everything that is given to you. So in the question, psi will be this portion, and then you have phi, which is corresponding to the CNF of the negation of the theorem, and then you have all the ones that are new because of the earlier steps of resolution. So there are three parts. But it doesn't matter which part it's coming from, as long as you can see two of the disjunctive elements being able to resolve, you can go ahead and resolve those two. So if you can eyeball and say, hey, this thing, has the negation of all of these things, and this one has all the non-negative version of all of those things, then you can just kind of concentrate and just kind of drill into those two. Is that okay?
And like options with like 3 terms or 4, you just concatenate whatever remains, right?
Whatever is left, yes. So when you have one variable or one term that is negated on one side and one term is one term is non-negated on one side and the same term is negated on the other side, that variable goes away. It does not get concatenated, but everything else will be concatenated. But in the result of the concatenation, if you have a variable and also the non-negated version of this, if you have a variable and a negated variable appearing in the disjunction, then that becomes just one. The entire expression becomes a one and it goes away. Yep. All right, so any other questions? So the first expression may be a little bit too much, right? For Boolean algebra. All right. Any other questions? Okay. If there are no questions, I am going to bring up something. We are running out of time for this class. We're running short. Okay, I wouldn't say running out. We are running short. Um, so instead of talking about lead code, which I really wanted to, um, so join the computer science club, for the lead code discussion because I think today we had a interesting problem, um, which is the parentheses problem. Do you want me to mention it because I think some people in this class may be interested? Maybe? Okay. So the problem that we were trying to solve today is lead code. Um, what's the name? Parenthesis is part of it. 22. 22? Yep, generate parentheses. So for those of you who kind of like a challenge, this is a interesting problem. My solution did not work. Okay, my solution that I was trying to work out, during the time when one of the students was thinking out loud, so I couldn't quite hear my own voice. Oh, no, it wasn't you. um, but it's hard to think, when you're hearing other people's train of thought. So anyway, I have the solution now. Okay, I have a dirty solution, but it's gonna work. So the question is, if you are given, in this case, three pairs of parentheses, okay, so you have open, 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 close, close, close. How many ways can you arrange the parentheses such that it is still valid? So you cannot close, you cannot have a close without an open. That's it, okay? So what would be the approach to solve this problem? So I have a solution already, but I don't want to mention it because I think all of you should kind of think about it. It does have something to do with what we do in this class. Okay, so I'm going to just do this one last part here. It has to do with experiments. And in this case, the experiment is um, open paren versus closed paren. Each character is sort of an event. Yep.
So if you were trying to do this, wouldn't you want to like hypothetically make a count that's related to both sides of the for the
Yep.
characters? So then you would have a count that goes for the left side and a count that goes for the right side. And if those counts are equal, then you should have the correct, like ideally the right close and open.
Almost, because you need those counts. You cannot have, okay, so instead of two counts, I would suggest to have one count. Every time you see an open, you add one. Every time you see a close, you subtract one.
I guess you could do it like that too.
But that's even better because if that count ever goes negative, that's invalid.
True.
Or if at the end, if it is non-zero, it is also invalid. Right? If you count, like every time you see an open, you add one. Every time you see a close, you subtract one. So if they match, at the end you have a 0.
Mm-hmm.
But you can also have a really weird match like this. This will still match because you're saying -1 plus 1 is also 0. So if that count ever goes negative, you can immediately say, nope, this is invalid.
Okay.
Okay? So that is a very important idea, okay, is to qualify whether a specific pattern is valid or not. Okay, but that part does not relate to this class, right? We never talked about matching parentheses in this particular class. But what we did talk about is now you have 6 slots, okay? And each slot can only be an open or closed paren. So if you were to brute force and you ask, I have 6 spots. Each spot can be an open or closed parenthesis. How many ways can you arrange the open and closed parentheses? In other words, I would consider open, 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 open to be one of the possible things because you can end up with that. So how many ways can you arrange open and closed parentheses when you have 6 slots? What would be the answer to that question? Remember
It's like a lottery problem.
it's not quite the lottery problem. It is more like
problem.
it's more like a coin toss problem. Okay, imagine you have 6 coins, okay, or 6 coin tosses. instead of head and tail, you have open and closed paren, right? So I don't care whether it's valid or not. I just want to enumerate all the possible ways to have open and closed parens. And then you basically, one event is a coin flip. And the possible outcomes of each um, trial is open or closed paren. So how many possible outcomes can I have when ordering is important? How would we figure that problem out? It's not permutation. This one is easier. Okay, so from the perspective of a tree, the first trial has two possible outcomes, right? What about the second trial? The same two outcomes for each node from the first trial, right?
So that's 2 to the 6th power.
So it would be 2 to the power of 6, yes. So you have 64 possible ways to fill up 6 slots with open or closed paren for each slot, right? But you end up with a whole bunch of those being stupid, right? Because you can end up with, okay, that doesn't make sense. Still doesn't make sense. Also does not make sense. So what you do is you take each one of the 64 thing, and then you go through that logic that you also talked about earlier. You go like, does that make sense? Nope. Toss it out. Does that make sense? Nope. Toss it out. Does that make sense? Yep. Keep it. So this technique actually has a name. Can anyone guess what is the name of what I just said? It's actually a fairly well used approach in what we normally call weak AI. It's called generate and test. It's a brute force approach because the generate phase generates everything under the sun. But the test phase says, okay, wait, hold on a second here. Some of these do not apply, get those out. So the generate and test approach is it can be considered a brute force approach because there's a non-brute force approach to do this problem where you only focus on the correct and the valid combinations of open and closed paren. But that algorithm is considerably more complex than what I just described. So this approach is not friendly because what is the order of time here? What is the complexity of this algorithm? It's 2 to the power of n. So this is really bad because it's not n squared. It is not n to the power of something. It is a base to the power of n. But yet, at the same time, the code is fairly easy to write. And if you look at the generate parentheses here problem, they have a limitation. Okay, constraint is n has to be less than or equal to 8. Because because otherwise it would take a long time, because it's exponential. When n equals to 9, it would take twice the amount of time compared to this one. Well, approximately, because you generate that many cases. How many cases get to pass through, we don't know, but it will still take the same amount of time to check whether a pattern is passing or not. So there you have it. All right, so sort of related to this class, sort of not related. So with this class, I think last time I showed you guys an example, and I said that I would do it by hand, right? So let's do that. And all right, so we'll go ahead and make a new page. And I think last time we were talking about omega 2 of A, B, and C. Is that correct? Maybe. Yep. Okay. All right. So the first thing we want to do is to go back to the definition of omega, and then we'll try to follow that code, just manually by hand. All right. So we are looking at counting. It's the very last part of counting. All right, so we are looking at permutations, and that's omega. The other one is big U. All right, so we're looking at this algorithm here, and omega. I mean, the I is not zero at this point, so we can go for the recursive case. And what I want to do is to show both the equation and the work we are doing side by side. Okay. All right, so the first thing we do is we basically say there are 3 iterations to this loop. How do we know there are 3 iterations? Because if you look at this code here, it says for each element of T, blah, blah, blah. And how many elements do we have in T? In T, in this case, how many elements do we have? We got 3 elements, okay? So we're gonna say, E can be A, and then E, okay, so maybe it's better to use a more nested format like this. E can be B, and finally E can be C. So line 2, 3, and 4, each one is representing one iteration of the big U notation because E has to be bound to one element of T, and there are 3 elements in T. Okay, so when E does equal to element A, what are we going to do? Well, we evaluate the rest of this thing. So we have to evaluate a singleton set with A in it, and then we have to Cartesian product that with omega 1 of T minus E. Well, T is A, B, and C, and E is A, so we only have B and C left. Is that okay? So that's for one iteration. Whatever this iteration ends up with, okay, so I'm going to put parentheses around this entire thing. We are going to union it with whatever the next iteration has. So the next iteration has something that is very similar. It's just different because in the next iteration, E is B instead of A. So that means the singleton set only has B in it. And then when we perform the recursion, we have AC in the leftover of for omega 1. And then for the last one, the only difference is E is C instead of B compared to the second on the second line. So now we have E being C, so the singleton set only has C in it, and then the leftover would be A and B. Okay, so I'm going to pause here to see if everybody is okay with this. Are we okay so far? Yes? Okay? So all of these operations are well defined. Okay, Cartesian product, yep, we know what it does. Union, we know what it does. The singleton sets, A, B, and C, that's easy. It's just a set with only one single element. So what we now need to resolve would be ohm1, ohm1, ohm1. Okay. So we take a look at ohm1. So ohm1 of, let's say, B and C. Okay, I only need to work out one, and then you guys can see the pattern, right? So with this one, we have 2 iterations because we are still binding E to each element of the set. So in this case, E can be B, E can also be C. Okay, when E is B, then we have this sub-expression of B being in the only element in a set, and we are going to make a Cartesian product of this set with ohm1 of, let's see, so B is out, so we only got C left, like so. And this is going to be unioned with the next one, which is having C in a set as the only element in the set, and Cartesian product that with omega 0 of the set of B, like so. So are we still doing okay so far with this? So next, we have to resolve what is ohm0. So ohm0 of the set B, C, it doesn't really matter what the set is, because according to when the terminating condition of omega, omega 0 of whatever is a set with just the empty tuple. Is that okay? So let me just write it out, okay? So this is going to be the set that only has one element, which is the empty tuple. So set of empty tuple and then ohm 0 of the set of B is kind of the same deal, just that. Okay, so we have now hit the end of the recursion. So what do? We substitute, right? Yes, we go back. So we backtrack. So technically speaking, when you are following branches, to the terminating point of a node, so when you get to a leaf of a tree and you go back, it is called backtracking. So we are now backtracking. So when I'm backtracking, I can look at this one here and go like, oh, we know what that is, because that simply is just a set with an empty tuple in it. So is this one. So that becomes a set with the empty tuple in it. All right. So now what do? We have everything that we need to evaluate this. So what would be the result of that? So what do we do when we perform the Cartesian product? So let's review that first, okay? From some of the expressions, I think it's a good idea to review Cartesian product. So let's just say that we have a set of AB and we Cartesian product that with 1, 2. So what would be the result of this? It's going to be a set, and what kind of elements do we have? They're all going to be two tuples. So we have A1 as a two tuple, A2 as a two tuple, B1 as a two tuple, and then B2 as the last two tuple, right? Okay, so that means, when we look at something like this, we're going to have, one single two tuple in it. So what is that two tuple going to look like?
Blank.
Yep. So there are two ways to look at this. So we can say this is, the two tuple is going to be with an empty tuple next to it. That would be the proper answer if, we support nested tuples. So the other one is going to be, if we support nested tuples, we'll get to that in just a moment. So if we support nested tuples, this is going to be the set of a tuple, and that tuple is going to take C as the first item, and then the empty tuple as the second one. Is that okay? But then if we do not support nested tuples, then the tuple, the empty tuple goes away because it's not, we cannot support it. So that goes away, and that also goes away. Is that okay? So now we have a straight up union, and what would be the union of these two items? Okay, so let me get here. This would be a set of two elements. The first element is a tuple with only B in it. The second element is going to be C as the only item in the tuple, like that. Are we still doing okay so far? Okay. So now we have just solved what is ohm1 of BC. So we now put that back into where we first referenced ohm1 of BC.
And with that same logic, then you can kind of just already figure out what AC and AB would be.
Yeah,
like.
yep. So that's a very good observation. So you can now say ohm1 of AC is just going to be a set with A being the only thing in the tuple, and also B is the only thing in the tuple. Oh, sorry, C, like that. And then ohm1 of, what is that? Last one, AB, is just going to be a set with A and B, each one being the only thing in a tuple in it. Is that okay? All right. So what do we do now? We backtrack one more time, right? Because we now say, Okay, we have just resolved what is ohm1 of BC, ohm1 of AC, also ohm1 of AB. So now we can back substitute. Okay. So we take the result of ohm1 of BC, which is this portion, and then we go back and say, this whole thing, I need to make sure that I got the right inclusion of parentheses. Are we good? And then this one is about the same. The only difference is instead of BC, we have AC. So I'm just going to do it the more lazy way like this. And then this one is going to be just AB. Is that okay? So now what do we get? In other words, what is A Cartesian product with the set that has B in a tuple and C in a tuple like this? What would that be? And if I tell you ahead of time that we do not support nested tuples, what is that going to look like? Well, okay, so first of all, if we do support nested tuples, what is that going to look like? A by itself, because A comes from one side of the Cartesian product, and then the tuple with B as the second item, because that's coming from the other set of the Cartesian product, and then we also have A and in this case C in its own tuple, like this. So this would be the answer if we support nested tuples. But if we do not support nested tuples, we basically just dissolve all the extra parentheses and only have the outermost one left. So that means, if we flatten this structure, then we basically only have AB left in a two tuple, and we only have AC left in a two tuple. Is that okay? Yeah. All right. So that means this entire line here is this as a result. Are we good? What about the second line? What is that going to look like?
BABC.
Yep, it's going to be BA, BC in a set. So I'm just using the format here, BA and BC in the set. And then the last one is going to be CACB. So we'll go ahead and copy and paste and just change this to CACB. And now we have just unions to perform. Do we see any overlapping between the three sets that we are unioning? Are there any common elements? There are no common elements, right? Because AB and BA are considered two different elements. They're not the same because the order is different within the tuple. So we basically just end up with the 6 elements all in one single set. That would be the final solution. Is that okay? I mean, are there any questions about how I just did the entire recursion thing by hand? Okay. So are you guys convinced that this particular algorithm is going to work? And the only thing it does rely on is we do not support nested tuples, so tuples can only be flat. We cannot have things nested. We cannot have a tuple nested within another tuple. All right. Are we okay at this point? Cool. All right. So this is Wednesday already. On next Monday, I can talk about the U function, which is also recursive. It's defined recursively. The only difference, the main difference between the union thing is, in this case, the union is actually going to work. Okay, it has to combine the same elements and not repeat elements. And this time the recursive call is in here. So we are basically looking at each element of the recursive call in order to do something. So it's a little bit different in terms of structure, um, but the basic idea is pretty much the same as the earlier one. Is that okay? Over the weekend, I know we are done with the lecture at this point. So over the weekend, I want you guys to spend some time on the next reading module. So we are pretty much done with counting. The next reading module is discrete probability. So this one is um, interesting in its own way because it starts off with the birthday problem, which we talked about already, and then it talked about the coin toss problem, which is going to be a good starting point. So the coin toss problem is asking, I posed that questions already. So this is a typical coin toss problem or coin toss type of question. Is if I toss a coin 5 times, if I flip a coin 5 times, what are the chances that there are 3 heads and 2 tails? The ordering is not important, okay? So this time ordering is not important. So that means, head, 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 tail, tail in that particular order versus head, tail, head, tail, head would be considered the same. Well, let me think. Nope, they're still distinct. We count it as 2, okay? So ordering is still important, but we are only interested in the count. All right? So let me say that again because I misspoke earlier. Counting, in this counting, ordering is important. So when we ask the question, what are the chances that you end up with 3 heads and 2 tails, you have to count all the different ways of ending up with 3 heads. So head, 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 tail, tail would count as 1. Head, head, tail, head, tail, excuse me, head, head, tail, head, tail, right. It's going to be another count and so on. So you have to add up all those counts and then divide it by the total number of ways that you can end up with after 5 coin tosses, which is 2 to the power 5. That becomes the probability. Is that okay? So I'm just trying to give you an overview of what kind of stuff you would get into. There's also Pascal's identity, which explains Pascal's triangle. Okay, if you're already familiar with Pascal's triangle, this will explain why that math works out. And then we have binomial theorem. And then in here somewhere, we have proof by induction. So proof by induction is introduced in this particular module as a proof technique. This is the second proof technique that is super important for computer science. The first one is proof by contradiction, which we talked about already. This is proof by induction, which is also a very important proof technique in computer science. So I'm just going to give you this much, kind of overview. So as much as possible over the weekend, try to read as much as you can into this particular module. And then on Monday, we're going to start with the discussion here. All right. Okay, so have a nice weekend. I'll see all of you on Monday.